Thank you for the introduction. As Mr. Chairman said, my name is Thomas Künstler, and my co-workers mainly from Materials Center Leoben, and also from Ceratizid, a hard metal producer from Austria, and a company that makes hard coatings. And I would like to tell you something about damage in structures that are hard-coated and have a very hard substrate, thanks to carbon cold hard metal. It's a composite material of hard face from say 80 to 100%. Those white areas here, tungsten carbide grains. The dark areas you see here is a cobalt that adds to the toughness of the material. I'd like to tell you something about residual stress and damage, how they are interacting, how we could model their interaction or show that it is very relevant to understand the residual stress buildup, because we do a lot of process simulation in terms of industrial production processes. For example, fine blanking, in which you have a metal sheet that you cut, or in milling. And in those processes, it's very interesting to understand the degradation behavior of hard-coated tools, structures in general, and because we want to exploit those supreme wear-resistant properties of hard metals that are even hard-coated even better. In metal working tools in general. The general framework of our research is state-of-the-art, where you make a part out of a steel sheet. For example, you have a tool and process design, you have a certain idea how you want to make the part, then you do process simulation, and if you are do it a little more advanced, you may also do finite element tool load analysis. It gives you an idea about the exact loading of your tool with lateral resolution, also maybe in depth within the tool volume itself, and you can correlate it to tool damage mechanisms. And if you have good indicators what to look for, say, in instrumented data of tools, then you can even think about the next step that we currently plunge into, so to say. It's tool health monitoring that facilitates things like adaptive process control or maintenance on demand for certain well-known, or to us well-known production processes. Well, we could show some of those damage mechanisms already from milling. I give you this very placative example where we there's a milling insert, a cutting insert, in which this is very far, but I could visualize this usually with my body, where the chip flows over the cutting edge like this, and we could show that there's a lateral correlation of an emergence of residual stresses. This area here is this area here, where we found in this direction a buildup of tensile residual stresses, and when there's local plastic deformation. And we could show also that this area with this tensile residual stress buildup is correlated in lateral position with the emergence of the first cracks that emerge in those tools. So we were able to show that this buildup of tensile residual stresses is very, very crucial for the degradation of the tool. Well, then if you want to design your tool in general as a tool maker, or a hard metal producer, or a hard coating applicant, you're always interested in where do the cracks start? Do they initiate within the coating, in the substrate? I've been working quite some time now with this material here. Where do cracks initiate? They do initiate here. I can tell you hard coating people from Leoben also found that they may initiate within the coating, of course, or this is very likely to happen. But I'm also showing you today something about the interface or closed interfacial fracture that may occur in a aluminum chromium nitride coating that's applied with physical vapor deposition on a hard metal substrate. If you have that information, you can improve your residual stress design, your post-treatment of the coating, whatever. You may be able to influence within the production process of your tool. So what did we do? We took a specimen that is notched, with also an FEM setup of it, and we loaded it under R minus infinity, so with this kind of pattern, stressed over time. And then we looked at the notch root, and we modeled and investigated experimentally the residual stress buildup of an axial direction of this kind of specimen. So we provoked local plastification in the notch root, watched the residual stress evolution before and after loading in specimen to avoid influence of specimen buckling. And then we compared, and we also looked for damage to learn. Well, residual stress, we did some simulations, we parameterized a material model to be able to make sure that we model the deformation behavior of our hard metal correctly. What you see here is what is it called? A number of flow curves in hard metals that we obtained in such a specimen, macroscopic specimen. We can see that there is plastic deformation before fracture under compressive strain, with elevated levels of RP, of flow strength, and there's a pronounced difference in this kind of behavior depending on the carbon grain size and binder content. Well, if you then do cyclic experiments, you find that for different load levels, you will have input for the parameterization of a material model that is then used to represent or reproduce or predict, or whatever you want to call it, the deformation behavior of your specimen. I forgot to say it was a 98% coated hard metal. And then you compare, make sure that your model depicts the deformation behavior correctly. And then, if you have that, you can go into your model with a certain geometry and say, apply my force 200 times. That's where hard metals in generally saturate their stirring response. Saturates, the residual stress buildup should be complete then. And then we saw that with a certain amount of plastification at the notch root that we provoked, say 0.05%, is close to the measurable detection limit of plastic deformation in the experiments. We get a residual stress buildup of, say, 400 or so megapascal. And with a little more plastification, we end up with more residual stress in tension, positive values. Well, if we now look at experimental validation of those results, we took two specimens that were uncoated, two that were coated with aluminum chromium nitride coating. That was about 2 microns thick. Loaded it for 200 cycles to 2 different load levels. Then we also, this is an overview of what we did. We have U is uncoated, A is coated. We say U1 star is after 200 cycles of a certain stress, 2 star for the higher load. This is just for you to understand the next graph. And one time with the coated specimen, we also performed more cycles. See what happened. This is also called 2 star. Okay. So what did we find? We found residual stress in tungsten carbide. This is the phase where it's more easily determined due to physical reasons. Well, we found that before loading, we had a certain compressive residual stress in the substrate. And after loading, there was this change in residual stress towards tension as predicted, or as is reasonable to assume, within the notch root. And this here, the lengths of these arrows correspond to the predicted change, and you see the actually occurring change here. So it's predicted rather reasonably, let's say. And the differences are, with the small plastification, the differences between simulated and experimentally found values are, well, they're there, but the agreement was very good for the larger plastification value. So our material model works fine. This will come in very handy when we want to simulate real production processes and damage of production processes, say in fine blanking tools. Because in there, it's very important to know where residual stresses occur and what they will mean for damage for crack growth, as I showed you for the milling tool. Well, if we have now a coated specimen, we see that after 200 cycles, these symbols here, the residual stress buildup is, this here is again the one experimentally found in uncoated specimens. The length of this bar here is a little below the one found for the uncoated specimens. But if we say we apply the same stress amplitude of 100,000 cycles, it's then again at the same level or even a little bit above the level found for the uncoated specimens. We think that this is due to the retardation of plastic deformation, due to the purely ceramic coating, which is very purely ceramic and has a higher yield strength than the hard metal that contains metal. thing I want to point out also, you remember that here we had 2000 megapascal watt in compression in the substrate, and here it's lower due to an annealing process in the PVD plant. You know, there's a 550 degrees maybe for an hour or two. So there's a stress relaxation. There's maybe another reason for the kinetics that are slower in this shift of the stress towards tension. And what comes in really interesting now is for the coated specimen with more load, we have then a rise in the shift towards tension that is not as large as predicted for the uncoated specimen. Remember, the 1.7 gigapascal were predicted, and here's only 1,000. And here you see it stops at 0. What is the reason for this? We looked at the specimens closely at the notch root. We looked at the surface and saw, well, there are no cracks. In none of the specimens there weren't any cracks really visible. This is what here just ripped off arc-related droplets, those holes, but there were no cracks visible. But what we did find in the subsurface state when we did perform FIB cross-sectioning in a groove here, you see here, this is the axial direction of the specimen, this here, and we applied some protective platinum to prevent curtaining in our cut. And what we saw, we did see some subsurface cracks. Some may originate from the grinding. Some authors in the hard metal community showed that already, that it may be related to grinding. But this here is new. This here is, well, an interfacial crack. We cannot really say it's close to the interface within the coating. And it is very similar to the cracks that Mr. Ustinkoff in the laminated materials section showed yesterday. Its maximum openings in the middle, so it may have originated here, and it goes here parallel to the interface of the coating. And if there's an inhomogeneity in the coating, maybe, or some weak spot, it will deviate eventually. This is, in my eyes, the early stage of the coating delamination, and is very relevant to failure. So, colleagues from Leoben showed that if there's a droplet, cracks close to droplets may occur. We now show you that here is a possibility also in hard-coated tools, being this may be the early stage of failure, and we also demonstrated below the surface there can be an origin for failure. So failure in hard-coated tools is situation dependent, temperature dependent. We don't know yet, but this is an interesting story to feel hopefully the researcher's life to clarify. And well, for take-home messages, I've already 3 for you. We can really, in an experimentally parameterized material model, we can use to model residual stress buildup tools and real components that are, like I said, fatigue loaded. And if you have a certain cyclic load amplitude in those structures that I showed you, even on the pure compression, you can have, of course, if you have a notch, trigger tensile residual stresses and have cracks parallel to the interface. Well, and these residual stresses, if they're reduced to a certain level, you may think that there are cracks involved. We found those cracks, and we think that there must be rather numerous to provoke this effect. We tried also with scanning acoustic microscopy to find them, but our surfaces are too rough, so we think that's the reason for this phenomenon, but we couldn't really show it for large areas, but we think it's rather reasonable to assume that. Well, thank you, and if you have any questions, please ask them.